All right, great. So, hi everybody. Welcome to Advanced Telemetry for Interplanetary Systems. Right out of the gates here, I'm going to just strike advanced from the title here because after watching the talks and everything, everybody here knows a lot about this, and there's very many smart people here that know a lot more about telemetry than I do. However, I can bring expertise to the table in terms of strong, eventual, consistent systems, peer-to-peer systems, and what we're calling, for the sake of this talk, interplanetary systems. So about me, I go by Mark Robert Henderson for SEO purposes. If you Google Mark Henderson, you'll see why. But I work for a company called Equilibrium now, and I'm working on the Rust implementation of the Interplanetary File System, or IPFS. I was formerly at Haya Networks. I have a startup called TallyLab where we put all these peer-to-peer ideas to the test on a consumer level. And sometimes I blog or publish my notes from talks and specs and things like that at mrh.io. You can also find me on GitHub at AphelionsZ, Twitter at mrh_io, and there's my website at the bottom. And this is just like, my opinion, man. So here we go. So what do we mean by interplanetary? This is admittedly a colloquial, almost a marketing-based term, and it comes from the Interplanetary File System, which is built by a company called Protocol Labs. In practice, this means that you're generally talking about peer-to-peer networking and peer-to-peer networks and systems in general, and the idea of strong eventual consistency, which I'll unpack in a second. This is not to disparage the work of like NASA and SpaceX and the ESA and the CNSA. However, the European Space Agency, or the ESA, has used IPFS for their telemetry. And there's a blog post by Rüdiger Klan, I think is a former ESA worker, that shows how they used a combination of clever JSON formatting, the CBOR encoding format, and this deflate algorithm to get, if you look at the last line of this, less than 1 byte per sample of telemetry. So that's pretty impressive and pretty cool. So just keep an eye on that. I'll post the link in the Slack and on like the notes for the talk and stuff like that as well. There's also the concept of what is a peer. And a peer is interesting in the concept of peer-to-peer networking. A lot of people are familiar with peer-to-peer from like Napster or Kazaa or LimeWire, or if I'm dating myself, BitTorrent. The idea here is that it's not quite a client, it's not quite a server. Sometimes it acts like a client and requests computation or data from other peers, and sometimes it acts like a server and provides those things. But really, a definition that I like to look at and use when I'm designing architectures is that it's a node that has all of the business logic and all of the computation of the full system in and of itself, and hopefully as much of the data from the entire system as possible, completely independent of the other nodes. So it can work on its own, but works best when it's connected to everything else. What is strong eventual consistency? A lot of people are familiar with the idea of eventual consistency from things like Mongo and other database systems, where you have this liveness guarantee where so long as all the peers are connected or all the nodes are connected, you're going to get all the updates from all the other nodes eventually. What strong eventual consistency adds is what's called a safety guarantee, which is when you get all those nodes to send you their updates, you will also be able to reconcile the same state of the database as all the other nodes via a sorting or a consensus algorithm. In an interplanetary system, if you're thinking like Voyager 2 or something like that, you may never receive another message from another peer ever again. There's no guarantee that, for things far out or even on Earth, for some reason, that you're going to be able to connect to them. But when you do, you will have the guarantee of having the same state. The tools that we'll be looking at in this talk here are tools that, I try to use every day, which is IPFS, the Interplanetary File System, our good friend OpenTelemetry, and a database system called OrbitDB that I'm an active maintainer of. So first, let's look at OpenTelemetry. This is the one that I admittedly, coming to this, know the least about. It was introduced to me by organizer Paul. First off, I just want to, if we can get some hearts and claps in the Zoom chat right now for the organizers and for the other participants and everybody, I just want to take this moment, since we're OpenTelemetry slide and we're talking about Observe, to just say thank you to everybody. So show them your gratitude, please. This is awesome, and it's awesome that we were all able to come together. So keep them going. Keep them going for yourselves too. Everybody's awesome. Anyway, in the spirit of Observe 2020, OpenTelemetry, we have a standard set of compatible tooling for tracing metrics and hopefully soon logging. I saw some beta stuff about logging in there, so good job, OpenTel team. And it's compatible for exporting with systems like Jaeger, Prometheus, Zipkin, et al. So we're looking at that. The foundational layer here is IPFS, or the Interplanetary File System. This is a great tool because it takes all the ideas of peer-to-peer networking and file level block storage and rolls it up into one tool. What it gives you are two main primitives. The first is peer-to-peer networking. It uses a library called libp2p, which in turn uses what's called the Kademlia distributed hash table. But to the layperson, that's just the routing and the peer discovery and the swarming and the pub sub messaging that BitTorrent uses to do its peer-to-peer stuff. So under the hood, that's all running in IPFS. But then what you have is a block storage layer. This chunks data for easy storage, transmission, deduplication. But the most important property is that all this data are content addressed and versus location addressed. So if you think of like a URL that points to a website that you visit, that's something that's location addressed. That's telling you where it is. The problem with location addressing is that if it's pointing to an IP address, that IP address can change if the DNS record changes, or if it's pointing to a file on a server or a script on a server, a file can be re-uploaded, the script can be rewritten. However, with content addressing, what it does is it takes the hash. There's different hashing algorithms, but for example, it could take the SHA-256 hash of a block of data, and then that becomes the address of that data. So if you request that hash, you get that content back, and that's a guarantee that you have in that system. The problem here is that it means it's append only, because if you change the content, then the hash is going to change. IPFS has some works in progress for mutability, but what we do is we use a different tool. We use OrbitDB for that. OrbitDB uses something called conflict-free replicated data types, or CRTDs. And a lot of people here probably know what these are. These have become popular in the last few years. It's a version of event sourcing, and it uses what are called logical clocks to sort database updates and achieve identical state across multiple nodes. You're writing to something called an operation log or an op log, and those have clock values inside of them to do that. In OrbitDB, the state machine is modular, meaning you can pass your own sorting function in, and it gives you the ability to create these flexible data schemas. So out of the box, we have document stores, we have key value stores, we have logs, we have what we call feeds, which are logs with the capability to delete entries, and simple counters as well. And as of today, announcement, it's now instrumented with OpenTelemetry, which I'll get to in a second. But first, let's just look at an example of a CRTD, just so we can get kind of our heads around how this is going to work. assume we have 3 nodes in a peer-to-peer system. A, B, and C are their IDs. And to keep things really simple, we're just going to use a counter. So the nodes are able to increment a value or decrement a value. You can use a use case. Perhaps in the current pandemic situation, it's just the number of people in the hospital right now, and you're tracking hospital overloading. Maybe these are 3 hospitals, A, B, and C. A is going to start off, and we're just going to go through sequentially what happens. B is going to decrement, B is going to decrement again, C is going to decrement, B is going to increment, but then something happens to C where they lose connectivity and C drops away from the network. Since these are parallel processes, life is going to just continue right on, and each of the nodes are just going to continue making updates, including C. C is going to just assume like everything's fine. It's going to continue business as usual. And then sometime later, C rejoins the swarm. The question then becomes, what is the state of the data at this point? What do we do to reconcile all this? And the first thing that we can do is assign each of these updates their own clock value. Now, adding numbers here, and the thing to notice here, when I say clock, I said logical clock as opposed to a wall clock. So this has nothing to do with the turning of the Earth. This has nothing to do with the Earth going around the sun or any Unix epoch or a UTC timestamp. These are just monotonically increasing integer values that each of these nodes individually increment as they make their updates. And to sort them, they all have to agree, and using what's known as a Lamport clock, named after Leslie Lamport, what we do is we sort first by the clock values. So that's going to give you a list like this. And as you can see in red, there's ambiguity as to which of these things came first if we're just sorting by clock values. So then we sort by the node ID to eliminate the ambiguity. And then you have this nice ordered list of updates that you reduce down to the database state. And just a shout out here, I mentioned Leslie Lamport there on the right, and then Martin Kleppmann is on the left, and a lot of this work that's rolled into OrbitDB is due to their research and their work. So shout out to those folks there. So what about the telemetry part? Well, I'm happy to announce that we now have the Open Telemetry plugin for OrbitDB. You should consider this a call for contributors. So if anybody out there is looking at creating distributed systems, is looking at using their tracing expertise, their observability expertise, this is your chance here to hop in and join the fray and get some good insights out of these peer-to-peer networks. It is something that indeed is lacking in this corner of the industry for sure. Although IPFS does have OpenTel HTTP support as well. So all those powers combined, we should be able to create something great. Just finishing off here with my observations thus far of the limited time that I've spent working on that plugin. It's probably been the last 2 or 3 weeks or so. So first, you cannot rely on consistent node connections. There's a famous 5 laws of distributed systems or whatever, and the one that says that these nodes are going to come and go is absolutely true. So the idea, again, you want to hold strong eventual consistency in mind. Assuming that the system is working as intended, you want everybody to agree on how to reconcile all the changes, and you want to reconcile them as fast as possible so that all the nodes have both all the business logic and all the data within them and can relay information through themselves to other nodes that need them. As far as Open Telemetry is concerned, we're finding that the tracing spans are kind of becoming spread across multiple nodes. I think Dan Diala's talk is going to blow these observations out of the water here, but I'm going to say them anyway. you're gonna have spans that are opened by one node and closed by another, and some of them may just never end. Like in the case of the Voyager example before, you might open a span there and expect that node to close it, and it might just disappear forever. So there needs to be a way to account for that. And I think the traditional client server thinking may fail you in the end. These peers are so hybrid and events are happening so fast. Like, one node connects to another, but is that a bidirectional connection? Is that one just requesting a connection? So we might need some more constructs and more nomenclature moving forward. I don't want to be the person that just shows up and says, everything has to change, but that's just one thing I noticed as I was working through this stuff. And tracing of distributed systems will require distributed tracing. So we're going to need both multiple nodes being able to write to the same tracing database or exporter, but something like using OrbitDB as a collector for tracing data is a compelling future work kind of researchy kind of thing, where the tracing data is both updated by multiple nodes but also distributed across in a consistent way all the nodes as well. That's it. That's my talk. Again, I'm Mark Robert Henderson, and for future work here, I invite everybody to contribute with me to the OrbitDB Open Telemetry plugin. Adding metrics to OrbitDB is another thing that I'd like to do in the future, and as I mentioned, using OrbitDB as a collector itself is a compelling avenue to go down as well. So that's all.